a summary of my thesis that I did, which is the impact of 100% renewable electricity on the hydropower generation in New Zealand. Do I push the space bar or something? The arrows, okay. Okay, that's the research goal. I think everyone's aware that a few years ago, the government's had a goal of going to 100% renewable electricity. And so we had just looked at what effect that would have on the hydro resources. This is my data sources. So I got the expected electricity generation in 2030 from the Electricity Authority off their website, which they posted in September last year. The electricity demand in 2030 was based on the Electricity Demand and Generation Scenarios report, which MBIE did in July 2024. And the expected electricity generation and demand in 2030 are built up from the actual electricity generated during 2024 from the Electricity Authority's website. So the data sources. And this is a summary of the generation investment pipeline up until 2030. So it's into two groups. You've got committed projects and actively pursued projects. There was a third group, which was called other projects, which is not included here. The committed projects are when the unconditional final investment decision has been made. So these are pretty sure these are going to go ahead. The actively pursued projects, there's been a start on developing these, but there's a big question mark whether they're going to go ahead or not. So, and in the other, it's unlikely that those projects are going to go ahead. So it's divided into the years and the different technologies. I would like to point out the difference between committed and actively pursued. The total, you're looking at about 1350 megawatts here for committed. And for the actively pursued, it's more than 10 times that. There's a big difference between committed and actively pursued. Also, just here, there's battery as well. We've got 200 megawatts and 200 megawatts. There's not much battery included in this. But I'm not looking at battery in the study, but just to point that out while the table's up. This is a picture of what that table was about. So the black bars are the committed, the red are the actively pursued, and the gray are the other. So you can see very little committed, quite a lot of actively pursued, most of it in 2030. There's a reason for that, which is shown in this slide. This slide just shows the committed and actively pursued by technology now. So the yellow is solar, so there's quite a lot of solar through the years. Blue is the onshore wind generation, and gray is your offshore wind generation. You can see there's a lot of offshore wind generation here, and it's all in 2030. The rest is from solar, a lot of solar, but as I pointed out in the previous thing, a lot of that is actively pursued. It's not guaranteed that this is going to go ahead. Goes through a bit of the method and approach. We took the 2024 electricity generated. Any new plants that were introduced during 2024, we stripped them out because they will affect the average for the year. And so we got a normalized electricity generation for 2024. And then we used that as a basis and drew up the 2030 electricity generation based on what the investment pipeline showed us. This is 2024's electricity generation on an hourly basis and on a monthly basis. So what you see here, the blue is the hydro. You can see it's varying a lot. It's giving you base load and peak load here in 2024. And it's giving you about 55% of the total electricity generation. The top here is in terawatt hours. I don't know if you can read it or if it's too small. The terawatt hours, and there's percentages. So the blue is the hydro. This gray here is the geothermal. The green is onshore wind. Red is solar, and orange is wood. and the black is thermal. The top one is the gas, and the bottom one is coal. That's on an hourly basis, showing it on a monthly basis. You'll see that in winter, for the total, the black is the total electricity generation. In winter, there's high demand for electricity. We had a dry year last year, so you see the hydro drops off during winter, during the winter months. This is the geothermal, the gas, the coal, onshore wind, solar, and wood. So the gas and the coal are making up for the increased demand in winter and for the drop-off due to the dry year problem. This is a summary again. We've been through it already now. It's just giving you a summary between the different plants that we've got between 2024 and 2030. And then this is the onshore, offshore wind farms. Cogen plants, I don't see any change happening between 2024 and 2030s, very low power output. And for the thermal, we've got about 2 gigawatts that's been produced by 7 plants. And I'm assuming that will go to zero for 2030. This is the demand, where we got the demand, how it's going to increase by 2030. So this is from MBIE, their report, EDEGS report. It's based on about 40 terawatt hours during 2024, and they had 5 different scenarios. And these are the increases in electricity demand by 2030 based on these different scenarios. I just want to point out here, there's quite a big ramp up here. This is in 2030. We looked at just the growth, which is the middle one, the pink one. You're looking at about a 23% increase in demand there by 2030. But I'd like to point out what's happened in the last 15 years. We've had a plateau of electricity demand. In fact, it's even maybe dropping slightly. 2024 looks the same. 2025 is probably going to be the same again. But that's what we based our study on. So this is 2030 now. The first scenario I'm looking at is if only the committed projects go ahead and we have a 23% increase in demand, what will happen? Firstly, you'll see we need a lot more hydro than we generated last year. We need 33.6 terawatt hours, where we generated 22.7 last year. That's not going to happen, okay? This dotted line here is the maximum power that the hydro plants can produce. In winter, it's going over that lot. So this, wherever it crosses that line, there'll be the demand is higher than what we can generate by the hydro. I'll just point out as well, the black is 2024, the blue is 2030. So that is for the power requirements, and this is more for the energy requirements, the hydro storage. So this is 2024's hydro storage. This is 2030. If we had to go by this, you'll see we very quickly come down to the hydro emergency level, and we don't really recover from that. So this scenario is unacceptable. It won't happen. We can't convert to this. If only the committed projects go ahead. The next one is if the actively committed and actively pursued projects go ahead, except the offshore wind, because the offshore wind is such a big part of this. You'll see that the total hydro required is a lot less. It's slightly less than what we required for last year. You see it's more focused in winter. There's less required in the summer months than in winter. It's focused that's because you've got a higher demand in winter, higher demand for electricity in winter. The other effect is that in solar, you're getting a lot less electricity from solar in the middle of winter than you do in the middle of summer. It's about a difference of about 4 times. You're getting about a quarter of the amount of electricity in winter as you get in summer from the solar. You're also getting from onshore wind. There's a dip in winter. You're getting less electricity from the onshore wind than you do in the summer months. I'm not sure why. It must be wind effects. And so the hydro has to make up for that in winter. And so it puts a high demand on it there. So there are days here where we don't have enough hydropower and can't match up to the demand. And you'll see what it does for the hydro storage. we were fine in the beginning, and it brings it down really hard to slightly below 2024. And then it recovers well afterwards. This is almost a balanced situation, that we're just on balance between demand and generation, yeah. But I just want to show you what happens when you get this kind of balanced situation. This is 2024. That is the hydro, and the blue is the wholesale electricity price. You can see the wholesale electricity price ramping up as the hydro storage comes down, and then it comes down again as the hydro storage starts going up again. So it has a dramatic effect on prices being balanced. And then this is if the offshore wind is also developed. Yeah, you'll find the hydro is providing no base load. Yeah, it's only providing peaking now. Peaks. And you still get a few hours where there is, you can't supply the demand, but the hydro's storage is hardly affected, yeah. But this comes at a price, which I'll show you here. The first scenario we can ignore because it's not going to happen. This is the more balanced scenario. This is the scenario where we'll definitely can cover our demand. But what you find here is that we're producing a lot more electricity than the demand. There's about a 38% excess. So there's a huge amount of overbuild happening here. A lot more generation than what's required. A lot less hydro required, only 7 terawatt hours compared to 22.7 in 2024. And there's a lot of time when no hydro is required. Almost 60% of the year, no hydro is required because solar and the onshore and offshore wind are providing you with your base load there. And it shows that the demand is being met there. And so that's our conclusion, is the study shows how the hydro changes from providing both base and peak load to just peak load as you get more and more intermittent generation happening. That's assuming you don't have any additional storage. This can be reduced by having batteries, having storage, either pumped hydro or batteries. That has to be taken into account, but you need a lot of storage. As I showed you at the beginning there's not much battery in the pipeline at the moment. And that you need a huge overbuild of solar and wind. And that's it. Thank you.
Okay, any questions?
Hey, Philip. Thanks for your presentation. The offshore wind in 2030, is that a specific project, or is that when it'll come online, or?
That's based on 7 projects that were in the pipeline. And it's a huge amount, 6.2 gigawatts of power. So it's huge. And that's all actively pursued. None of that is committed at the moment.
Hi there. Thank you very much for your presentation. You mentioned that there is very little battery capacity in development or being pursued. Is that including or excluding the potential for pumped hydro to fill that kind of role as a medium to long-term sort of energy storage option?
Okay. There was a lot of interest in Lake Onslow, that pumped hydro. It's a huge project. I mean, if that came on board, you'd have enough storage, but I haven't taken that into account now. The batteries, we're looking at 400 megawatts of batteries in both committed and actively pursued. That's not much at the moment, but that's what was in their pipeline. I don't know how accurate that is still. That was from a year ago.